Hey, folks, enjoying the course so far?
Yes.
Yeah. Good.
Of course.
So let's get started. In this project that I gave you guys, I've given you first things first. Whenever you create an application, you need to manage some config information. I've externalized all the config information into a Bootcamp config YAML. YAML is a format in which it's increasingly common to store config information if you want to store it as text. Right? So it is just a colon separated format and indentation matters. So for example, here, database. I'm using a MySQL database, things like that. Right? Something or the other, you can do that. So I won't go over that very much.
But
now,
a couple of questions on this, YAML.
Yeah.
One is Elastic, it says index name. Is that the same as user ID, password ID, something like that?
You have to mute yourself. Somebody is not mute, guys. Please mute yourself.
That was me, sorry.
Yeah, what's your question?
Elastic, over there,
Yeah.
you have documents. Index name is documents and then the password.
Yeah.
What is index name, Asif? Because
yeah. So
is the same as the username password or what?
No. And see, what in relational schema you call a schema name, in the Elasticsearch you call the index name. Okay, that's what it is.
Okay.
So you have to create an index into which you'll index.
Yeah, okay. That is one. And the others, right at the start, we say device is CUDA. For those of us running locally, we just substitute that with CPU?
Yeah, CPU. Yeah, wherever you see CUDA, if you don't have CUDA, replace it with CPU. Okay. And those of you who have machines here, some machines have the NVIDIA GPUs. And if you weren't early enough in forming your team, you were penalized by being given a machine that might not have it. In which case, you're most welcome to put a 4090 into it, which you can later on take with you. Right? But jokes apart, guys, this bootcamp at this stage is very lightweight. You can do it with the CPU. But as we make progress with the homeworks, you will need much faster machine. The server is there, massive server with 4 GPU server, and you will need to do your work on that. I do regret that some of these machines don't have a GPU. I'm trying to arrange. There's a massive GPU scarcity. In fact, I don't know the story. Sukhpal, is it okay to tell the story? One of us got conned. One kid came and sold us a GPU. Right? And these are massive GPUs, $2,500 each. Right? Took the money, went off, and then the GPU doesn't work. Right? It's quite, there's a lot of, it just speaks to how much scale, well, fortunately, the warranty will cover it, and then we'll get another GPU. So, there's a huge scarcity of GPU at this moment. It's very hard to procure. Right? And almost all the vendors have jacked up the price. What used to be a 1400 GPU now goes for 2500 or 2000. Come Monday, NVIDIA is going to make an announcement. I hope that announcement brings some relief. We'll see. So that's that. Anyway, that's about the YAML file.
Asif, quick question on the YAML file. The YAML file, if you see the password, the root password and all that is like open and visible.
Yeah.
And like when we really do production scale and think about it, no, right? Okay.
You shouldn't have it. So guys, this is just for academic purposes. Never do this in production. Password should never be kept here in plain text. That would be a disaster. Right. Now, let me go. So, guys, please pay attention here. Right? And at this moment, please pay attention to the screen. The only package I'll walk through and where you should start, the root of all things, is the text package. You see the text package in SVLearn? Go in there. Now, let's look at the journey. I'll just draw out the journey for you.
Are you recording this?
Yes, it's being recorded. See, what is the journey? I asked you to go find a domain of text documents. Why is this? Domain of a little bit darker, maybe. Yeah, domain of documents. Pick a domain, guys. People in the last cohort, they have done very good things. One of them, Sushinda, that some of you know, he's from Tamil Nadu, a Tamilian, and very proud of his heritage. And in Tamil, there is this beautiful poetry, very wise, Tirukurals. So it contains deep wisdom. Any situation in life, there is a Qural for that. Right? I suppose that does explain why a mental depression and these problems are relatively rare. Actually, I'm yet to meet a Tamilian. I have a huge circle of Tamil friends, and I'm yet to meet one of them who has a long and sad face. So maybe it's the Qurals that's helping them. In North India is the Kabir's Dohas. So what our good friend Sushinda did is he said that this is a world's treasure. It's something that's captured in only one language, Tamil, which only a small proportion of humanity knows how to speak. But these are gems. Right? It should be more widely known. So he actually used exactly this bootcamp project. He made that the corpus. And he has created an application which you can visit, where you can ask questions in English and it will come out with give any situation. Tell me about this or that or situation, right? And it will come up with the best Qurals appropriate for that. Right? So think of it as an ancient therapist, ready to use, and it's there. So do something, guys. Do something practical. Don't just pick Wikipedia or something generic, right? Pick a good domain of documents. So much knowledge is available free. Actually, the best things in the world are just free. The priceless things are usually free. Qurals, for example, that wisdom of an entire culture is just available free, right? To download. And so all you have to do is enrich it, add value to it using a project like this with AI. Right? So do it for your whatever you hold dear. Do it for that. Right? I hope that you don't, guys, come back with some generic boxes of, okay, I did it for Wikipedia. That is like cliche. Right? Do it for something meaningful. So take your documents, D1, D, K, documents. Then what is the first thing you will do? Each document could be, you text extract, because these documents can be in any format, PDF, it could be in PostScript format, doc format, docx format, PPT format, God knows. You need an extractor to convert each of them into a .txt, isn't it? A text, plain text. So you need an extractor. Now, pick your favorite extractor. One of the ones that I would recommend that is very popular, there is an open source project called Apache Tika. This is written in Java. Apache Tika has been the workhorse of the industry, of the NLP world, for decades now, right? And it is very mature and very high performance, very fast, right? And to boot, it supports, I believe, 138, I don't know, you guys can check the exact number. I must be close to this. Document formats. I didn't even know so many document formats exist. Yes. So many, and by the way, this is not a joke. Have you ever looked at those object formats from Microsoft? It's indecipherable. If you just try to read it, it's hard to figure out what's in there. Right? All of these things, proprietary format, is that they have managed to somehow extract text out of it. Right? As you can imagine, it's a pretty massive open source project. So this is a good time to get introduced to that open source project. Now, it turns out that since many of you don't know Java, I'm sure those guys must have taken pity on you. So they have created a Python wrapper around it. I'm kidding. Right? So you can just do pip install Tika, but before you do that, or before you use it, you need to point it to where the ticker jar is there, because all it is doing is it's calling into the Java library. Right. So what it will do is it will extract all your document to plain text. That is a journey. Now,
So
by the
is
way,
it,
I spoke in
is it
favor of.
multilingual? Is it
Go ahead.
multilingual conversion, ticker to multilingual conversion, or ticker?
Yes, yes. I believe it supports some 38 languages or something like that. Check it out. I don't know why I keep picking up 38, but find out how many languages it supports. Just go to the website.
Okay, thanks.
Asif, I tried to test the extractor that you posted in the solution, and I didn't see it creating a .text file. Is it supposed to actually create?
We'll walk through it right now, and then we'll see. Yeah? That is that. Then you'll get what happens is it extracts the text and puts it in the database, right? Because it's one of those enterprise practices that, see, you don't create text flying around here and there. You have a central repository of your artifacts. Right? Another way to say it is that this is raw data. The moment you create text, you have spent compute power on it. It becomes a feature of your model. You put it in a feature store properly. Yeah. What is the next step about text? What can I do with the text? I just converted War and Peace into plain text.
Chunking.
Right? You need to chunk it. The War and Peace always reminds me of a joke. One guy comes and says, so my jokes are really bad, guys. Huh? My kids tell me that they're not just bad jokes, they are dad jokes to the next level. So one guy comes and says, I took a course in speed reading, and I read the whole of War and Peace in 5 minutes. So the other says, okay, explain to me what it is about. Oh, it's about a war in Russia. So something like that. So anyway, you take War and Peace, it's a long piece of text. So what do you need to do? Each piece of text needs to be broken up into chunks. Why do you want to break it up into chunks? Can somebody remind us of the reason? Why should a text be broken up into chunks?
Vector database, so you can compare your queries to it.
Very pragmatic reason. True, but very pragmatic. Give me a
Semantic, semantic units, right?
Yes,
Okay.
that is a good answer. Anyone else?
Meaningful boundaries, to create meaningful boundaries.
Meaningful boundaries. See, when you read text, human beings think as thoughts. It would be nice if one thought is captured in one chunk. If the text is too long, it contains many thoughts. If the text is too short, it doesn't contain enough. It's not semantically rich enough or dense enough. Right? It's half a thought or something like that. So semantic chunking is a topic worth thinking about. Semantic chunks. Okay? Do that. And the more practical reason is, even if you don't care about semantics, practical reason is your sentence encoder, every single sentence encoder has a boundary. Because it's an encoder, it has a token limit.
So that was the primary reason for chunking, right? The token boundary, the token limit wasn't that the primary reason why we had to chunk?
No, that's how people think. Actually, that's not the reason. You want to do semantic chunking. You want to capture no more than a thought in a chunk. See, look at any Wikipedia page. You'll see that many thoughts, like it goes from the history of a topic, right? So, for example, look at something. Look at Riemann hypothesis. Look at something. It will start with very succinct thought on Riemann hypothesis, what it is. Then suddenly it may start giving you the history of the Riemann hypothesis. Before you know it, you're looking into the life history of Riemann, right? And some mathematician said this, another mathematician. I don't know. It goes into a lot of different thoughts, right? Spanning multiple domains. The real reason for semantic chunking, see, the token boundaries will go away. Transformers are becoming big. I mean, the limits will go away. Transformers are becoming bigger and bigger. Today, you can get a transformer with 2,000 token limit, which is a very generous limit, right? Most of your text would actually fit into that limit. But the real reason to do, or 8,000 now token limits, but the real reason to do it is to capture one thought per chunk. That's how you should think, guys. Huh? So you chunk it into that. And then what do you do? Each chunk becomes, so these are chunks, C1, CM, chunks. Now, what do you do with each chunk? You embed it in a vector space, right? you do encoder. So you need a chunker, extractor, chunker, encoder. Does that make sense, guys? Yeah. Once you encode, what do you end up with? Lots of vectors, right? Now, where do you keep all these arrows? Where's your vector index? You need to index it into, and here, as I said, in this course, don't use open source tools for that. Home grow your own. So we will use a FAS index. You will hand build your FAS index using code, using the FAS library, right? And store it yourself and manage it yourself. See, in a way, right, you're doing things the hard way. Why? You should never use open source or any tools blindly. When you build it from scratch, you know exactly what is happening inside it. Right? And later on, once you have mastered it, yes, go ahead and use Llama Index or Pinecone or God knows whatever it is that you want to use.
So if the corpus is large,
yeah,
then it will take a lot of memory, and FAS lives only in memory. Right?
FAS index lives in memory. And it will, what do you mean by lots? Give me an example.
Like, would we exceed, like I have a 64 gig machine, would we go beyond that also? No.
You can put in 50 million documents and you would still, if you're doing your indexing carefully, there's no chance you'll exceed that.
So FAS again lives in memory, right?
Yeah, you can load it in memory.
And then we find a way to store it in secondary storage.
I mean, it's just a file. I mean, FAS is a index file is there. You load it to memory at runtime, but you store it in the file system. That's it. Just an index file.
So, if you use the library, right? You know the APIs that prepackage it for us, right? What do they give us in addition to what we can do with just the library? Like they give persistence that I can
No. See, that's a good point. What does a vector database give you? First of all, it relieves you of your unnecessary cache.
Okay.
Right. Besides that, which is its primary purpose.
Okay.
No, I'm kidding. So the first thing the vector databases do is see many things. Managing the index, adding at the same time, adding more data to it while searching. These bring issues of concurrency. These are traditional computer science issues, right? Server-side management, systems management, etc. All databases do that. So you bring in the database technology of managing multi-user, and read writes and so on and so forth together. They also give you some additional services like metadata. You can say that this document happens to be history. So when I'm telling you search only history, that kind of metadata filtering and so forth. But frankly, right, at this moment, vector databases don't give you so many services because they come with the extra baggage and the extra limitations. Frankly, I did the vector databases 4 years ago, 3 years ago, 4 years ago. Since then, I've been hand doing FAS index. Even today, I run parallel implementation for my homegrown FAS index management and vector DB. I use QDRINT. Right? QDRINT has matured. Only in this year, I can say that, okay, maybe I'll transition over. Right? But still, there's a compelling reason to. For smaller problems, or for like the use case in this lab, I would definitely advise you to keep everything under your control. Just run it off. If you do QDRINT, it's okay. You have to learn QDRINT. You'll never learn how these vector indices work. Right? You'll never learn approximate nearest neighbor algorithms. And by the way, ANN machinery is a remarkable piece of engineering. We are today, these ANNs, they have a throughput of close to 10,000 to 100,000 queries a second.
Wow.
Just think of the magnitude of traffic they can take. And such a wonderful piece of technology, instead of playing with that toy, it's like, you bought yourself a Ferrari and then you're saying, okay, let me have a chauffeur to drive me around in that. Right? It seems pointless.
So, just to sort of maybe trying to understand QDRINT a little bit, would it be fair to say it's some database to store, it stores a the indices in persistent storage, but it is uses something like FAS, like GPUs for the.
Of course, they all use FAS with some variant. FAS with HNSW, and so on and so forth. And I'll talk about it today. That's exactly what I want to talk about. I know it's getting a bit late today. I'll stretch a bit beyond 5. I'll talk about these things today.
Also, the pairs index, does that really boil down to like a list or an array
Internally.
internally in the code?
Mm.
So once you've generated all these vectors, what are you storing them into? Like
You call fast and you say store it, and it will store it.
and but then what would it look like? Would it just look like a list or an array or something?
Internally, no. Internally, it's a very complicated data structure, and I'll talk about it today.
Okay.
That's what I'll do. Vector is the core of vector databases. It is the core indexing technology. It is the ANN engine, approximate nearest neighbor search. But guys, hold your thought. I'm going to explain these things in detail. So we realize that our journey is made up of this, followed by indexer, right? Extractor, chunker, encoder, indexer. 4 pieces of. And finally, what do we need? A query. Query is what? You go to the index, fast index, and say, okay, here's my query. Tell me its nearest neighbors. The search, and that would be your search result. And therefore, you have a search engine. So what I would advise you guys is in the first iteration, forget about Elasticsearch, forget about cross encoder. You notice that I didn't bring cross encoder. I'm saying, so this is the data journey. Let me call it data journey. People often call it the ETL, right? Or the compute journey. Now, your query, how does your query look like? You create a little interface. I would advise you to use runtime. Use something very simple. Use Streamlit, right? Or whatever, a grad IO. Or if you're really adventurous, go use React. It's, right? So build your whole UI beautifully. But here's the request. Here's how it will be. You make a little UI. There's a query box. You put some text. That is a query text. What do we do with the query text? You transform the query text using an encoder again to get a query vector. Right? You get a query vector. Now what can you do with the query vector? You can go to the fast index and say, give me k nearest neighbors. It will give you k nearest neighbors, isn't it? Now, what it will tell you is the IDs of those neighbors. Well, you need to recover the text from it. You better have saved somewhere in a database or table or wherever a mapping from ID to the actual text, because you don't want to return some weird IDs to the end user. You want to return the actual text chunks, the actual chunks, right? So this is the simplest. At this moment, do the simplest implementation, guys. Forget cross encoder, forget Elasticsearch, forget everything. Just get this to work. So there are 2 parts to it. First is creating the index, and then at runtime searching the index with a little UI and having your own search engine. Yeah.
So Asif, I think up to this level, we had it working the first 2 weeks, right? But in code that is very prototypish. When we look at your solution, this is the real code. This is how code should look, right? Ours looks like a high school project, right? But when we are trying to fit it here, we are having some difficulties in getting it to work. Some of it, I think, you can just with the YAML.
That part is straightforward.
Sure.
We can sit with the TAs and
how do we? Is there a sequence in which we run the files?
Yeah. That's exactly. So see, guys, many of the questions that you have, just patiently wait for it, because I'll walk you through all this. So guys, what have we learned from this screen? What have we learned? For the sequences, first is data journey, because without index, you realize that the point at which it's a producer-consumer model. Journey, producer-consumer model. The journey, data journey produces vectors and puts it into the fast index. Right? It's a producer. Producer of what? Yeah, producer of vectors. Producer of vectors. And your GUI GUI that you will use is what? It's a consumer of vectors. What it will do is it will just take a query text and code, get a query vector, and just say, give me K and N. So give me means consumer. It's a consumer. So your entire architecture is a producer-consumer model. Does that make sense, guys? Right. And so you can actually develop it in parallel. One guy could be making the UI and doing the consumer part. Somebody could be. But what is your data producer journey? To summarize, data journey made up of 4 parts. First, gather data, create a file directory of data.
And that is pointed to in your YAML.
That's right. You point it in the YAML. Directory of documents. Then what's the next step? So first of all, gather. This is data scavenging part. Right? You go scavenge the web for data. After this, so this is scavenging. B, extractor. So the next thing you do is you run the extractor. What will extractor produce? Plain text. C, chunker. Chunker will produce chunks. But remember, when you store chunks, it is a good idea to give it an ID. Remember which document it comes from. Document ID, and then actual chunk text.
But the ID for the chunk comes from after you code into the model, like the vector code.
No, you create your own ID.
Okay.
I would advise you to use integer IDs. Use integer IDs. Why integer ID? Because FAS will need integer ID. Are we together?
When you are inserting into your database, you keep that ID as a primary ID, it automatically creates ID.
That is
That's good.
Yeah, whatever. So if you do auto increment integer, that ID is good enough. No, in fact, that's what the solution will use. So, but let's go logically through that. D, what is the next step? What do you do? Encoder. Encoder will convert this into vector embeddings. Right. What's a good place to store the embeddings? Once again, put it in your database because there is a one-to-one mapping between a chunk and a vector, isn't it? So you might as well, the chunk table, wherever you do the chunk table, you can have an ID. You can have a foreign key to doc ID, the text, the actual chunk text, and you can have the vector right here itself. As an array, you can store the vector.
Array of numbers?
Array of numbers. Now, see guys, do a very basic, don't worry about performance optimization and so forth. It's inefficient to store a long array as plain text, but go ahead and do it. Right.
So the foreign key to the doc ID, therefore, would mean we have a doc table and we just
exactly
all the docs, right?
Yeah. See, remember, you extracted the text from extractor, which gets the plain text out of it. Where do you store this plain text? Create a doc table, ID, text, full text, extracted text, right?
So the second table, we are also storing the vector information along with the chunk.
Yeah, that's right. Store the vector. You need to store it somewhere. So what happens, guys, this database in the language of machine learning or AI these days, it becomes your feature store. You realize that this is your feature store because all of these things, this text, these vectors, these chunks, they are artifacts. They are things that your algorithms need, isn't it? Now you ask this question, why should I store the text or the chunks or the full documents when I'm getting the vector? Well, because at the consumer part, and you will need the text anyway, right? That is one reason. The other reason is when you create a feature store and you save these things that you spend compute resources to create, advantage is other algorithms. Somebody wants to do a clustering on the data. Remember, that's the next project I was going to give you. Yeah, do classification and clustering. How would you do that? You can just, all you do is a simple read on the table. You don't have to go through the whole data journey. If your features are stored, yeah. So guys, in the ML operations, ML ops pipeline or the data AI pipeline, it is feature store has overwhelming importance, right? You can store it as a relational database. You can store it as whatever you want, Mongo, whatever, but feature store is important. There are also open source projects that are dedicated to storing vectors and features, right? One very good open source project, which at this moment I would say you can hold off on, but is Feast, right? You could use Feast. Try it out. At this moment, we'll give you the sample solution with SQL tables, relational tables, because I trust all of you have heard of SQL and played with basics. So the kind of SQL needed here is the most elementary SQL to read it. And to insert a
I use SQLite.
That's SQL, yeah, so long as you can store it to a file system, that's fine. SQLite, MySQL, we use MariaDB, MySQL, Postgres. I remember that in the last cohort, somehow Postgres was very popular and they all insisted that in the next cohort, I should make Postgres the default. It turns out I was too lazy to do that. So the solution is still with MariaDB. So guys, now what happens? You encode, what is the last stage of the data journey?
Face index.
No. Where do these vectors go? Indexer.
Face index.
Index builder. Index builder will put it into face index. So this is the data journey. And then the query, the consumer journey will come to later. So guys, do you see the sequence of events? One of you wanted to do that. Let us study the code in this sequence. Should we do that now?
Yeah, Asif, do you need to store the face index back in the relational database for lookup?
No, the face index itself is the core of a vector database.
No,
it is
to relate it back to the chunk, you need to have an index back to.
Yeah. So what you do is, so guys, yeah, this is an important question that, guys, please pay attention. Yeah. Let's have one conversation, guys. We'll have a break, then we can talk other things. So here's the thing. You have an ID, chunk ID, and you have a text chunk, vector. So you have this pair, this tuple. When you give it to FAS, the API, you give it this tuple. Are we together? So it will internally somehow store. So imagine, it doesn't do a hash map, but imagine as though it is some very high-end hash map. It will just maintain a table of chunk ID and vector like this, chunk vector. Hold on to your questions, guys. Let me answer this because I've gotten a question online. So you store this. So when you come with a query vector, what it will return is, so when you search for it, when you search the FAS index, you give it the query vector, and what you get is a list of IDs, right? In fact, you get pairs. You get ID and the distance from distance to query, to query vector.
Okay,
and you get a list of this. And because you have the ID, you can take the ID back to your FAS table. Yeah.
Okay, thank you.
Sorry. Yeah. Okay, somebody has a question.
Yeah, so searching for ID is better than searching for a large vector in the database. That's why this helps.
Oh yeah, of course. Okay. You don't want to search for a ginormous string.
And the other thing is that database is different from this FAS in-memory database.
See, FAS index at the end of it is a file, right? That you load in memory and it becomes your index that you search.
It's not a file on the disk. It's just a file in memory.
No, it's a file. You store it. Oh. You want to save it onto the disk, right?
Okay.
You do save it to the disk.
So first you do whatever SQL kind of a database, and from that you pick the IDs on the embeddings and then move them into this new database called as FAS.
Yeah, remember, you don't move them. What happens is a FAS technology, any ANN technology, will never store vectors as is. It never. It shreds the vector. Yeah. It shreds it, completely destroys it. But from the vector, it comes out with a more efficient representation of it. Are we together? right? So, guys, let me give you the intuition of FAS one way, or no, not FAS, approximate nearest neighborhood, right? ANN. See, guys, you have all been kids, and many of you have kids, right? And so, when you go to school and you say, I'm looking for my son or my daughter to take my child home early, what is the first question that the office will ask you?
Which grade?
Which grade? Exactly. And so what happens is, suppose all the students in the school were in one giant pile, then you realize that it would be much harder to search for your kid, isn't it? But because they are partitioned by grade 1, grade 2, grade 3, grade 4, grade 5, whatever it is. Now, let's take elementary school. Therefore, you go to that particular classroom, you know where that grade students are, and you are searching a much smaller space of students and picking that student and getting back. Am I making sense, guys? Yeah. So that is the concept of approximate nearest neighbor search. What they do is, they will, now let me explain it through other examples. See, suppose you have, like, this is the way you do, like, you're searching for a book or books similar to this book. You say, hey, I'm looking for a book on electrodynamics. The library, you don't go search the entire library. What does it happen? You know where the science floor is. Within the science floor, you know where the physics floor is. Then you know where all the electricity books are, right? And so you search for relevant books matching your need within just a shelf or two. Does this make sense? To do so is like the Dewey system of library, right? And all of this, what do? They make it very efficient for you to land in the vicinity of where the right answers are. But you're not doing a linear search. You're not flipping every book in the library one by one to see which one is relevant or about electrodynamics, isn't it? So to flip through every book in the library is to do linear search. That is why one of you asked, is it internally stored as a list? No, because then it would need a linear search, right? Even before AI came along, in computer science, the efficient storage of information, the word index comes from that, indexing, because what is a Dewey system? It's an indexing system for books, isn't it? The indexing word comes from there. You take any textbook, what do you find at the end of it? An index. You look up a word and then it will tell you which page it is on. Now in the page, you still have to figure out where, right? But you know exactly where to search, right? So all of these technologies, approximate nearest neighbor technologies, they give you an orientation of where to go. Next question that comes is, do they really, if they know where to look for, do they really need to store the vector itself? They don't. They say you store the vector. When you come to the vector, from that, we will extract some information that we think is relevant, right? So for example, if I know, so I'll give you an example of what it does, right? One of the oldest geometric quantity. So for example, when you put students in a grade, right? And I say, give me a student like this student. What you could do is go to that grade and pick a few students like this students and come back as search results, isn't it? Are you getting it, guys? That is an example, right? So the way, or another way to look at it is, if you're looking for a color match, there are millions of colors, right? But people can create color buckets like yellow bucket, red bucket, then green bucket, and then some in-between buckets. Make sense? And when you look for color, they're looking for your exact match within the same specific boundaries. It's just small buckets. That is all efficient indexing. Now, while these analogies are good, now let's bring it down to the ground, to real life. What you do, suppose you have a point, and let's take this in 2 dimensions. So I'm drawing it in 2 dimensions, but I am saying, imagine a d-dimensional space. So as you can see, I've drawn a d-dimensional space, right? There we go. Then let's say every vector, what is a vector? Vector is analogous to a point, because a vector, 1 and 0, the only thing you need to remember, where's the tip of the vector, right? It's a point. A point and vectors are the same thing. So let's say that you have points here. So you realize that when you embed vectors into the space, it will be a non-uniform distribution. Some areas will be sparse. Some areas will be extremely dense. Let's say you ended up there. I'll just take a particular embedding for some document corpus. Is this realistic? It could be, isn't it? And let's throw a few sparse here and there. This is how your the vectors are looking out in the embedding space. So now, if I get a query vector and I have to find the k nearest neighbor, how will I find the k nearest neighbor of that vector? Oh goodness, I'll have to find the distance to every other vector in this space. That's a linear scan. Linear scans are not feasible. Today in web scale, you are searching across 100 billion images. Yeah. And these machines come back in lightning fast. So obviously they're doing something smart, right? They can't be doing linear searches. What are they doing? Let's try to understand what they do. What you do in this space is, you look at this, and I'll give you one of the older algorithms because it's simpler, right? You ask this question, okay, there are 2 axes. There is x1 axis, x2 axis, and then, of course, as is clearly visible, there is x3, x4, x5, all the way to xd. Right? It's a hypercube, hyperspace, right? What you do is pick an axis. X1 is as good as x2. Which one would you like? Let's take x1, right? You look at only the x1 value of every point, and you're not searching for it, by the way. You're preparing your data at this moment. You have a bunch of vectors. You're thinking, what do I do with these? Right? You're imposing a superstructure on top of it. So what you do is you find the median of all these points. Now you notice that there is a big pile here. These two seem more or less balanced out. So where will the median along the x1 axis fall through? Would you agree that it will perhaps be somewhere around here? Like median is that line which divides the space into equal amounts on each side. Would that be a median line? Good median line, guys? Right, okay, so this is a good median line. Now you divide it with that. You say, okay, now it's easy. Now what we do is, you say, okay, now let's try x2, the other axis. I have 2 regions now, isn't it? The left region and the right region. Are we together? This line partition. So I have 2 partitions, both of which I'll partition along the x2 axis, but I will use the same methodology, find the median. So where will the median of the right part be? Look at this. It will be somewhere around. Would it be fair to say that it will be somewhere around here?
So that is the median of...
Like half the point should be above, half the point should be below.
Just the right side.
Just the right side. Does that make sense, guys?
Mm-hmm.
That on the right side, this is how you'll partition it. Right. Now, let's look at the left side. Left side, the line will be much more up. It will be somewhere here. Are you together? Mm-hmm. And then you would do it on the 3rd axis, the 4th axis, the dth axis, and then you'll come back to x1 axis. Now let's do it again. You do this one, and perchance you may decide that this is a good partitioning here, and maybe this is a good partitioning here. We'll stop here just for simplicity's sake. I'll just stop here. So how many regions did you end up with? 1, 2, 3, 4, 5, 6 regions. right? And you realize that I can continue this process, but you stop somewhere. Like, for example, you say, hey, I don't mind doing a linear search against a box of 100 vectors, right? An exact search against 100 vectors. Now you do one thing. A query comes, query text comes, you convert it into a query vector. What will happen to that query vector? That query vector is going to sit somewhere, right? Let us say the query vector goes and lands here. This is your Q vector by accident. Now tell me, guys, at this moment, if I'm just looking for 10 nearest neighbors, should I bother looking into box 4? No. What about box 3? No. What about box 5? What about box 6? And about box 2? Probably not even box 2. Right? I can just look in the neighborhood inside this little box, box 1, and find the nearest neighbors.
On what basis are you putting these lines?
Median.
Just median?
Yeah, median. So this particular algorithm is called KD tree. What does it do? It is based on a partitioning of the space, vector space, isn't it? But it presumes one thing. This sort of algorithms presume what? A notion of distance, right? You can't partition it, right? Unless you have a notion of distance, how far something is, and so on and so forth, right? So therefore, KD tree is one of the simplest of a whole set of trees or space partitioning algorithms that are called metric trees. There are many such, O balls and this and that, but let's stick with KD tree. So now there is a problem though with this thing. Suppose your query vector is here, this guy. So suppose your query vector lands, let me go here, lands here, Q prime. Look at this one. I want 10 nearest neighbors. So you pick this one, that looks good. You pick this. But what happens is you are missing some genuine ones, which are neighbors, but happen to be in the adjacent quadrant. And the rule is you're not supposed to cross quadrants unless you have exhausted all the points and you still don't have 10. Right? So what will happen is if you find 10, even if they are a bit distant, you'll end up picking those, isn't it? That is why the word that is used is approximate KNN, approximate KNN. By the way, the K is silent. People just write it as ANN. And right. So now you realize, so now can you explain or anyone can reason why the word approximate is there?
Because you might miss some genuine.
Exactly. These are not, there's no guarantee that these are exactly the 10 nearest neighbors. You might have missed a few, isn't it? Right. But that is the price you pay for fast searches, because this searching into it, by the way, you realize that you have reduced the problem by a significant amount, right? And so the trade-off in the industry has always been that you should see. I'll give you an example of how much of a trade-off it is. The loss in accuracy typically is like 0.01 or 0.001% in your search results, very minuscule, right? But for that little bit of sacrifice, the speed up typically is 4 or 5 orders of magnitude, right? So what will return in like 10 seconds will now return in 1 millisecond, right? Or less. You realize. So and I gave you one quantization, one approach to do it. In reality, the ANN is a whole subfield of machine learning and of computer science. People have come up with very smart algorithms to do it. Why? We deal with web scale data, isn't it? And we search for indices, images. We search for them. And so this FAST algorithm came from Facebook. There are a few competitors like Scan, etc. That is there. But FAST actually has many internal variants. The internal variants are that from the very brute force of notion of distance, it can use L2, that is the Euclidean. In this world, L2, wherever you see it, means Euclidean. Flat L2 means Euclidean space distance. Euclidean distance is as the bird flies. It turns out in higher dimensions, Euclidean distances are horrendously expensive to compute. Are we together? No. And you don't want to store it also like that, flat L2, because it's very big index file. What you do instead is you use more sophisticated manners. One of the ones that I would ask you to start with is IVF, but okay, let me take HS, Hierarchical Navigable Small Worlds Map. Hierarchical Navigable Small Worlds Map. So there is something that comes from graph theory, or rather complex graph theory. What it means is something like this. If you ever look at a complex network, like a social graph, you will see something very interesting. It has a fractal-like structure, somewhat fractal. Actually, some of these things started out with the initial work of a physicist, Barabasi, who has written a wonderful, wonderful book, which is freely available on the internet. It is called Network Science. Right? Look up Barabasi and network science, so I can put a link. What he observed is that when you make complex graphs, you end up with communities within the graph. When you think of social graph, it's obvious, right? But when you, or just think of the US roadmap, do you notice that there are clusters? Small cities have lots of roads going within the city, and then there'll be a highway connecting the cities, right? So you have little worlds, separate worlds that are interconnected by some edges. And if you zoom into those worlds, you will see even sub-communities, right? In network theory, you call them small communities or small worlds, right? And so think about it this way. If you think from a network graph theory perspective, if I give a vector, what do I need to find out? Which community it belongs to, which world, small world it belongs to. And I can search for neighbors only in its small world. Does that make sense, guys? To use that approach is this. Hierarchical, navigable, small worlds map. Means map the whole network. When you lay out, it will look like, it will be a map of the nodes and the edges, etc., isn't it? Right. So make a hierarchical navigable is inherent, like, you know, you have some way to reach each of the little small worlds or the communities of nodes clustered together. Think of them as clusters, except that in graph, because there is no metric, you can't really use the word distance, right? You use the word community, right? So these are your small worlds. So guys, do you get the intuition? It's a very powerful algorithm. Yeah. The intuition is these are the small worlds, so these are communities, and you search within the community. Go ahead.
So HNSW is one of the options within FAIS?
Within FAIS, yeah.
So right now we are using the flat L2, but you think that's very expensive for large data sets.
That's what everybody starts out with for some reason, because everybody feels, okay, I know Euclidean, let me use it, it's safe. Yeah? It's good, but it's brute force. Means there is no approximate about it. It's a linear search, right? Use HNSW or IVF, or there are many variants. There's some internal indexes. Use efficient ones. Your index files will be small, and the response times will be much faster.
So we found nothing for about 42,000 chunks.
Yeah.
The search time through FAIS was roughly 2 seconds.
And now you know why. Now you know why. You were doing linear search.
Yeah.
Right? Okay, very good. You guys are learning.
So quad tree is a type of KD tree, and that is used in mapping, right?
Quad tree, yes. Many of these, like there are many things. Open trees, cover balls, this, that. There's a long history. I mean, see, guys, if you just, if you're in a hurry to do a PhD, pick approximate nearest neighbor and come up with one more way to do it. Go ahead.
From the data journey perspective, when it comes to input data, once you have loaded this, and then say if you have additional data, then I guess appending is.
Yeah, you can keep adding to it. Keep adding to it.
And what about if there is changes to that input data, then do you redo it or there's an incremental way to just upload the changes?
You can do that. And that is exactly what these databases give you. They manage the indices for you. They know at what point, right, you should rebuild the index, very much like Oracle database. At some point, you have to rebuild the index. You do too many changes, it's efficient to rebuild it.
Okay. Otherwise, you can do small ones, you can do.
Yeah, we can keep doing it. Yeah. So,
So which one do I implement like this L2 versus this?
no, just use HNSW or IVF. IVF is another good choice.
Is that like an enterprise, a small index?
Yeah, no, these are production grade. I'm telling you, use FAS. See, FAS, there's nothing small about FAS. FAS is easy to use. See, algorithms like FAS, scan paper came from Google and all its variants, right? And especially more than that, what they give you is the engineering infrastructure to do it right. Within it are the core heart of it, these indexing technologies, HNSW, IVF, and these things, the result of many, many years of research. When you look at ANN, you're talking about 30, 40 years of research producing one of these engines. And that is why these engines are rock solid and they bear the kind of traffic that is unimaginable, right? They take web scale traffic and they just work like a charm and their memory footprint is negligible. Right?
So Asif, can I ask a question there?
Yeah.
So we started with the initial corpus, right? So and then we created the face index and all of that is done. But let's say I add more to the corpus now. Do I only do the indexing for the newly added one?
Yes.
Do for the...
What you do, absolutely, sorry to interrupt you, but yes, what happens is you have an incremental process. New document comes in. See, the right way to do that is you have a directory or a source and you have a listener at the source. Don't do it now for this project. It will be a little bit heavyweight engineering. But in production, what you have is there is a place. The moment new document shows up, whether in the database or in the file system or wherever, or one is submitted to REST service or whatever, immediately this entire data journey is triggered. And incrementally, it gets added to the database, it gets added, the feature store gets enriched, the FAS index gets enriched, everything gets enriched. Does that answer your question?
My question was the last part, the face index, even that is only incrementally
incrementally added to.
Okay.
Yes. And that is it. See, these technologies have been very, very carefully crafted for industrial or mass. I wouldn't even call enterprise scale use because these days enterprise is called baby size. Web scale. These are designed for web scale use.
Okay. That was my question. Is it like
enterprise? Okay, guys. So are we together? Now, are we ready to read the code?
Can I ask one more question before you go into reading the code? I know you said don't worry about Elasticsearch at this point, but just for my understanding, the Elasticsearch piece was to do the traditional search as against the semantic search, right? Or is there another purpose to it?
No, see, okay, maybe I'll answer that question today. See, here's the situation. People call it semantic search or dense search. Vector space searches are dense search versus traditional search. Elasticsearch is that inverted keyword search, inverted index search. Those are sparse searches. Why? Because it's a lookup map. Roughly speaking, it's a fancy hash table. Right? The simplest way of thinking about it is that all the traditional search engines are fancy hash tables. I'm not belittling them. There's a lot of technology. Like, for example, Lucene is one of the marvelous pieces of engineering. Elasticsearch is a wrapper around it. And Lucene as an open source project is absolutely worthy of worship. It has been the search engine driving the enterprises for decades. Now, having said that, conceptually, they are just keywords to document mapping, inverted indices. We talked about that. Now, what happens is that if your query is semantically poor, right? If I just give a word or two, keyword, and there is not enough information, then a keyword search does better than semantic search. Why? Semantic search, there is not much semantic. For example, if I give the word apple, can you tell whether I'm talking about apple fruit, apple computer, or there's a British a phrase, you are the apple of my eye, mom will say to a child, right? So what apple? What apple are we talking about? You talk about bank, is it a commercial bank, river bank, or is it your aeroplane banking? Semantically, there is not, because see, AI and everything that I've taught you says that a word picks up meaning from its surroundings. There was no surrounding, right? But an elastic search or the traditional search will remember that in this enterprise, I have much more document about, because I'm dealing with farmers, I have far more documents on farming than on computers, right? And so just because of the statistical preponderance of farming documents, it will bring up the most relevant farming documents, right? Apple as fruit documents. And so it will outperform AI search. So the gold standard has been, which is that is what I call hybrid search in my spec, is that when a query comes, you search in both. You search in keyword index, right? And you search, and you can use Elasticsearch because it's most common. But by the way, you don't have to now. There are libraries that implement only the core of it, the core algorithm, the VM25, I think it's called. Just gets the core algorithm for inverted search, sparse search. Do that, and then you get the semantic rich vector search. Now you get two sets of search results. What do you need to do then? Then you use a high-powered transformer. It's called a cross encoder, to find out, re-rank all of these search results and to pick the best from it by comparing it to the query vector. Are you together? Right? So then you get the best of both the worlds. Right? And generally, this is just a tip of the iceberg. See, what happens is search systems, right? A typical search. It's a scatter-gather approach. You scatter it to multiple search providers, like result providers. They provide candidates. You come back with the candidates and you re-rank the candidates and then you serve, right? And if you get search, you will immediately realize that search architecture and in many ways advertising architecture are the same, right? Think about it this way: if every product and user are carefully embedded in some vector space, you realize that the same ENN technology tells you what to recommend. Recommendation engine, advertising, everything becomes possible, isn't it? You are the user. What should I recommend you? Go to the embedding space, find the items around you, recommend or advertise to you or do whatever. Right? So there's a very close connection between all of these ideas, and they are all the same ideas, of which this is a consequence. I don't know if you guys know. I think I can talk about it. Yes, some of the leading music streaming companies. This is how they do recommendation. Right? Literally, this embedding space and the FAS and all this technology you're looking at, literally is what is being used to provide song recommendations and so on and so forth. Am I making sense? Yes. Okay, go ahead, Mridha.
That was my question actually on that hybrid, right? You can implement the two.
Yeah. And you can implement other things. So 2 is minimum. Take the best of both the worlds. Why not? Right? So that's but for this first homework, let's not do that. Right? So guys, now it is 5:15. We have a choice. Would you want me to read the code next week, or do you guys have an hour or two for us to do code walkthrough today? Next. How many of you for next week? Almost all of you. Oh boy.
Include me as well as.
Okay. All right, guys, if you want, so then what we can do is, see, the code walkthrough is important because I'll give you the structure of the code and so forth. So guys, okay, let me give a brief, at least a starter idea. You go into this code. How would you read now? Which of these files should you read first?
Just curious. I thought we did this last week.
Yeah, we did this last week. Yeah.
Oh, we already did that, is it?
Yeah, we did the code walkthrough last week.
Yeah.
I talked about the text extractor.
Yeah, you went through step by step, every step that you outlined.
Oh, I did that code walkthrough. Okay, wonderful. If I've done it, nothing to do. So the heart of this is, what is the heart of the text extractor? You just go and use this Apache Tika, right? And from the Tika library, you convert it to plain text, you store it, right? This one. So remember, this is the core internal library that does it. Chunker. Did I go over the chunker also? Chunker will chunk it. Sentence encoder.
Yeah, you did.
What sequence do we run this?
In that sequence, literally. I mean, see, guys, all of you keep asking me what sequence. I am a little bit at a loss. Like, this is it. This is the sequence to run it.
So are you running file by file, or is there a main thing?
So now comes the question. Yeah, let me do that. So this is the inner core. What you do is you go to the compute directory, and this is something I'll have the TA sit with you guys, or maybe do an extra section for all of you. Now look at this. For every job, do you see there is a job? Text extractor job.
Yes.
Right. This is optional, guys. Huh? You can, what it does is, see, I'm giving you a taste of real life. In the enterprise, documents will come at you furiously, like thousands at a time. You can't be doing one and then another and then another. That's not the way it works. What will you do? You need a parallel compute engine, a distributed parallel compute engine. Spark is has been the workhorse of the industry for a very, very long time. Right? How many of you know Spark? Okay. How many of you have at least heard of Spark or known Spark? Now it's everybody. Okay. So Spark it is. Right. This is the Spark code. What it does is this will do exactly that. If you look at the heart of it, all it does is it use the extractor. Oh, look at that. Somewhere there must be an import of the extractor. Oh, look at this. Text extraction library from the text directory, right? See, here's the thing, guys. I'll tell you a tip. In Java, in Python, quite often you don't even need to read somebody's code. Just read the imports.
Sir, some people are confused about svlearn folder. Can you please explain where is it and how can import our own code?
Okay. svlearn folder is in the root directory. When you unzip the file, right there, you'll find the svlearn folder. Anybody who is not seeing the svlearn folder, speak up.
Asif, I just downloaded that, and your folder structure, the contents of svlearn are not the same to what is there that is downloaded. You have a lot.
Yeah. So what I'm showing is the complete solution, which I have not released. I've given a partial one. I could, I suppose, open that folder. Let me see, comprehensive. Yeah, bootcamp. Okay, let me do that. I'll open the one that you guys have, but it would be the same. Let's see what it has. Here is the svlearn.
Yeah,
are we
that's
together?
not the contents that's currently. I just downloaded it from support vectors.io, and it does not contain a folder called text.
It is inside svlearn. I literally see it here. What is nobody able to see the text folder?
You can see the text.
You are able to see it. Okay. So why?
The reference that Rafael gave me.
No. I think you accidentally. I sent you the different class folder.
Oh, that explains much.
Yeah. See, guys, let's go through the steps. It's very, very straightforward. You go first to the course. Which of these courses are we in at this moment?
Yeah.
This one, are we sure?
Yes, sir. Yes. LLM Projects.
The one with the balloons. Is the one with the balloons? We go into the balloons. We go into semantic search. Let's go to the first day. Oh, we go there. We see recording, etc., lesson plan. Okay, let's go to the second day. There we have attention, blah, blah, blah. Let's go to the third thing, Streamlit chain. So I'm introducing these technologies and library for nearest neighbor, scikit-learn, etc. promptly. So these are baby steps we are doing in the beginning. And then RAG, which am I in the right project? Yeah. Bootcamp. Oh yeah, here we go. Partial solutions. Literally, there is a whole day called partial solutions. It's a 45 MB file. Do we see here? Is this what you guys are downloading?
Yes.
Right? So the easy way to go to it is just go to the course portal, and look for this big card called partial solution to project one. So, Sarah, I think we misled you.
That gets me back on the right path. Thank you. I was off watching butterflies.
So we go here and we, when you unzip this, then I suppose you look at this, right? Then we get here, as we learn text, and the compute is what we are talking about. So guys, this is it. To get this, I'll give you guys a lesson. If you have understood the text folders, it's good that I covered it already. All you need to do is pick up basic Spark, PySpark, and then it will become obvious to you what this code is. This code is not doing anything. It is taking a whole directory of files and in one parallel distributed compute, it's converting all of that whole directory into what? Plain text. That's all it is doing.
So we'll have to install Spark and
PySpark, yeah. Okay. The Spark and PySpark. And for that, I suppose I'll make sure that we post instructions if you want. But start by reading Spark. Right. Once you do that, I think there's a README here. Okay, the order in which, so somebody asked, what is the order in which we read it? There's literally a README here. Do you see that? Text extraction job, chunker job, indexer job, vectorizer. No, this is the opposite. Okay, ES indexer, that's okay. Chunk and ANN indexer, this is correct. Then today, this week, guys, forget about the service, forget about the consumer part. Right? Oh, actually, you can't do that. We need to make sure that the following services are running. So there are these services. The way I think our TAs have restructured it a little bit. And what they are saying is that everything, chunking, extracting, everything has been made into a service. So the Spark job will just call the service job, services. Now, services are microservices. So I suppose that means that first read the REST. In REST, go to Fast APIs. You guys are familiar with Fast API. You can learn Ray later. Do you notice that there is a results re-ranker fast search sentence embedding service? If you give it text, it will return you the sentence embedding of the text, right? If you want to index some text, you can give it a fast, right? And it will do it. So can I recommend, don't worry about running all of this. Take time from the TAs, guys. Reach out to Chandar. He will help you set up this whole thing.
Is Chandar in
India? Okay. Chandar is in India time zone.
Okay.
Reach out to Chandar. You can also reach out to Harini, but I think for this, Chandar would be more appropriate because he'll walk you through the whole structure of this. Bring up the services. Run the compute jobs, that's all. But if you, so hold on guys, but here is what I would suggest. Before you learn, go learn PySpark, go learn Fast API at least, how to write REST services. While these are learning curves and you're still ramping up on this, in the meanwhile, you can do something. Nothing prevents you from going into the text folder and taking, let's say, text extractor. You see this text extractor, right? What can you do with the text extractor? You give it a path, a file path, right? You have a PDF on your file system, guys. You have a PDF on your file system. Can you just directly feed it to this class and get the text out of it? So play with each of these classes, learn how to use it.
Also, I did exactly that, but again, right, when I converted the PDF to the text file, I didn't know what was happening, where the text file was supposed to be.
It is returning you as a string. Look at the return value. Okay. It is giving it back to you as an in-memory string. It's up to you. You do what you want with it.
Okay, so I can actually store it in the string variable?
It is returning you. You can literally say, so for example, if I were using this code, you could literally, well, okay, so I've kept my keyboard away. You can literally say text extractor T and then T dot extract, I think what's the name of this method, to text. Give it a file path, and in return value of that will be a text, plain text. That's it. Simple coding, right? Is the return value of this function, the plain text. You see how simple it is. It's literally the return value as plain text. Yeah. So guys, even before you go doing Spark and REST and all that, at this moment, I would say, you need to be intimately familiar with all the facilities in the text folder. Do it, guys. Write little experiments, little bits of code. Now, see when it chunks. I mean, when it does a text extraction on the PDF, are you happy with it? What junk do you notice in there? What is it that you have to go and clean up of? In AI, nothing comes free. You will realize that when you convert a PDF into text, you will end up, suppose it's a book on physics. In the beginning, there will be copyright information. There will be, he's the publisher and that guy is the, whatever it is. Lots of junk information will be there at the beginning. That has nothing to do with physics, isn't it? So you will learn something. Namely, you need to do some data post-processing. Isn't it, guys? Right? You can't just blindly take the text and go chunking it. So you learn something from that. Now, whether you do that or not doesn't matter. For the simple, in the beginning, you can just ignore doing that. Let's go again to the chunker. What is the main? See, I've made it simple so that all of these are one-liners. Look at this method called create chunk. Do you think we understand what it is doing?
Takes in a string, gives us a list of strings.
You've given comments as well below, so it clearly says.
Yeah, exactly. Quite literally, it tells you what it does, right? So things like that. So can I write little experiments to play with it and see it work? You can.
But Asif, you said those vectors will not be returned as a list. They need to be put in a database.
We're not doing vectors yet. Remember, from plain text, you're creating smaller texts, chunks. This one is a chunker, no? Look at the class. It is the chunker class, chunk text.
No, so I think they understand the ideas in the text folder. It is all the proof of concept ideas.
Yeah.
And the other
core ideas. Yeah.
Then if you go to the SVL and the
computer
is the application. The text is what we can play with.
Yeah. So what you can do, so for example, compute, you don't know PySpark at this moment? Forget it. You can just write your own private loop to read a whole directory of documents and extract text from it. Can you not? And create another directory of just plain text. Isn't it? You can then write another little bit of code that will read a directory of text and convert it into chunks. You see that, right? So, and slowly you could be picking up PySpark, you could be picking up REST and so forth, if you don't know that. So take an incremental approach, guys, especially those of you who are coding, getting back into coding after some time. Take an incremental approach. Remember, you have the whole of two more months. Right? Take an increment. It is easy, but it won't feel easy because I've dumped a lot of code on you. But do small experiments.
Sit.
Yeah. Is someone saying something?
Sorry, that was my cat.
Asif, I have a small question.
Yes.
About the metadata.
Metadata of what?
Yes, so this is the classic steps. This is okay that you will create, all the steps that you told. Chunking, embedding, vector storing. But for the metadata, for example, I have 5 books and 5 books have their IDs. So it's just, we are looking in a metadata is a kind of spreadsheet where it has IDs and the book name and the author name, that's it.
It's totally up to you. What I'm saying forget about even storing the book name or the author name. If you want to, those are extras.
So, because I also find a blog in which they were emphasizing on metadata.
See, metadata is important because you can post filter. You can say that, hey, metadata filtering is a facility vector databases give you, because people say that only search in finance, only search in physics, only search in biology. Right? So that is metadata about a document that you index.
That is something separate that we keep.
You can just look at this in a database table. You can
keep metadata for running this code. It is something that is separate, right?
That's separate. And at this moment, I've simplified this whole search engine down to its bare essence, right? So when you say our metadata is important, yes, they are. But is it necessary for us to learn about this technology? At this moment, skip it. Don't worry about it.
So metadata, you can read whatever metadata you want. How many chunks are there in a table? How long did it take them?
Right.
Yeah.
Those kind of things.
And I was able to do all this. The metadata thing, I just didn't know why do we need it. It's just a separate thing that we.
So metadata can be useful from a traditional search perspective, right?
Absolutely. It is very useful. Guys, I'm not devaluing the importance of metadata. They all are helpful. The question is, should I add it to the spec of your project? At this moment, I've kept your project bare bones because our goal is to learn the core essence of a search engine before we start putting more flesh on it. Right? So learn the essence, guys, first. Learn how to do it. Already it's proving challenging to half the cohort because many of you come from diverse backgrounds. So first master this. This code base that I've given you, yes, is it everything that is needed and essential for doing AI search in production? No, it's not. No, that's a different beast. But if you can do this, you can do that. Are you getting it?
If people want to do it, okay, go ahead. Use your creativity. Why not?
Yeah, yes, of course.
You know, if you have time and you have skills, why not? Go ahead and give.
Yeah, why not? You can guys blow it, but you will realize that many more projects are coming. And at this moment, you guys are all behind.
Yeah.
So try to first, walk before you run kind of thing. Finish what we have. So guys, also reach out to us for help. We'll help you. I'm here all day. You can come to me. And here's are there. Run these experiments first alone, standalone. You will get a feel for it. Then you will know that Spark is nothing but a distributed compute engine. What I did for one file, it just happens to do it in parallel for a whole directory of documents. No magic to it. That's all it is. You see the point I'm making, right? And then you ask yourself, hey, I have a text, I have a chunker. Why don't I make chunker into a REST service so that people can post on the web? Me a plain text and I chop, return the chunks. That makes it into a REST service, isn't it? And so there is a chunking service, right? Likewise, there is a search service and so on and so forth. Right? Now, is it making sense? Doesn't it? Yeah. So guys, here's the thing. I'm going to be here. I'm not going to go away. I'll end the session, but all of you who need help, I'll be here till whatever help you need, you have gotten from me.
Quick question. When we are inserting the embeddings into the database, what is the type of the data? Text?
No, you can store it as text. I mean, consider the embedding vector to plain text, right? Because in the database, you'll be better off saving it.
Retrieve it, it looks like a text. So do we have to
convert it back into numbers? Yeah, and that is one line of Python. I think it's all there. All that code is there to read it back. See, guys, I called it partial solution. In reality, it's the whole solution. All right. You just have to figure out. The only part that I haven't given you is to figure out exactly what is it that I gave you. But it's not a partial solution. I've given you the entire solution.
Yeah, sir. Actually, this is too much. Let people figure out by their own. You give it the whole thing. Last time in bootcamp, we did by our.
Yeah, the last bootcamp people, I didn't give so much of this. But this time I've given you the whole solution. You just have to learn to understand what is where and use it.
How are we doing when you compare us to the previous cohort? Where are we in the journey?
Different parts. In some parts, you guys are ahead. In some parts, you guys are.
Yeah.
So
I mean, there's the exercise alone.
In this one, at this particular moment, I think you're a little bit behind compared to previous cohort.
Okay.
That cohort came with a lot of deep coders.
Okay.
But that cohort also had many teams which were behind. See, don't compare because what matters is at the end you finish it.
Yes.
Right? At this moment, take your own sweet time to catch up. That's what I would say.
Sir, explain. Some people who finished last bootcamp immediately got hired.
Oh yeah, that is true.
You remember that?
Yeah.
Yeah.
Yeah, one thing I can tell you is whosoever finished the coding, others were noticing. And in this audience, last time, there were some entrepreneurs looking to hire, and they were keeping an eye on the guys who are actually coding.
Right.
And they ended up making offers to all those guys.
Were they experienced or fresh grads?
Fresh grads also.
I mean, any experienced folks in that?
Yeah, lot of.
Okay.
Lot of the experienced ones got hired. I mean, everybody who actually coded, right, got noticed. And because they got noticed, they immediately they didn't even have to leave this room. They got offer right away.
Wow. Yeah. That's something.
So guys, I know if you guys are feeling frustrated or feeling a bit lost, remember guys, I'm going to end the session now. In a few minutes, I'll close it. I will be here. Right? You want to understand things, come and I'll explain. Right? What I will do, how about this, guys? I'll take a 20-minute break and then I'll come back to the seat and one by one, you ask your things and tell me which part I should explain. Does that seem fair? Right? Let me take a 20-minute break.
Asif, if you are doing that, is there any way to record? Because again, like, there could be varied questions that others can make benefit of as well.
Sure, I'll record it.
Because again, unfortunately, I have to drop off, but I can definitely go back and review the recording. I'm pretty sure others are going to have the same questions that I may have. So,
sure. I will record it. Why not? Why not record it? Let me record it. So let's take a 20 minutes break and then I'll be back. And I'll be here, guys, till you have exhausted all your questions.
Another quick question. When is the next TA session for this class?
See, guys, there are multiple TA sessions. One is regular. For the Tuesday class, there is a TA session which happens on Monday, right? Regularly, every Monday, same time, 7 p.m. Pacific time, Kyle is giving a TA session. Are we together? Then, I give, well, not exactly a TA session.
Monday session, is it the same Zoom link? I never thought.
Same Zoom link as the Tuesday session.
Okay.
Right? So whatever you use for the Tuesday course, use it for the Monday course. Kyle will be there. A few other TAs might also drop in. They will, see, here's the reality, guys. We have made all these TAs available. You know how many people attended last Monday? Can somebody guess what was the attendance last Monday? 2 people, just 2 people showed up, right? Valuable resources accessible to you guys. Take advantage of it. Likewise, on Wednesday, I don't give a TA session, but I give a research paper reading. Like, for example, today I couldn't finish Lava. I will do Lava this Wednesday. I'll announce it. But the only thing to remember about the Wednesday session is, because I open it up to the general public, you don't get that warm and comfort feeling that all our conversations are internal. You have to be a little bit careful because it's being publicly broadcast to, I mean, actually, in reality, there are 30, 40 people there, but sometimes you have 60 people there based on the topic. But you have to be aware that there may be strangers present. Then I'm trying to arrange, so every day there'll be something. I'm trying to arrange for a Thursday evening session for you guys, for this bootcamp. If Thursday evening 7 p.m. works, does it work for you guys? Pardon? Thursday evening 7 p.m.
Yeah. Works.
Yes.
Okay. So I will arrange a TA session, another hour or 2 of TA session till all your questions are answered, all the help that you want is given. Let me arrange that for Thursday evening 7 p.m. Is that fixed? I'll announce it then. I'll put it on the course portal. Same Zoom link. Right? To the same Zoom link of the bootcamp, show up, you'll get your help. The only days that we don't have TA sessions would be Friday, Saturday, Sunday.
Okay. Thank you.
Yeah. Also, those of you, I know that many of you are taking the Tuesday course, so it's not fair to announce a TA session on Tuesday. Right? Otherwise, I could have arranged a TA session to run in parallel to our Tuesday evening class.
Are you still online? Quick questions.
I thought you'll stay back.
No, I have a question for you.
Okay, so all right, guys. So with that, I'll end the recording.